Hello everyone, welcome to my presentation. In this presentation, we'll look into various techniques to reduction in variance in simulation. So first we'll see what we have seen so far, and then why we need variance reduction, and then we will look into three or four journal techniques to reduction in variance, and then determining the number of runs. So first, what are we essentially doing here? We are having the random variables x1 up to xn, and we are interested in simulating the expectation of a function of a given random variable. So what we are doing in simulation, we are first simulating the given random variable and calculating the value corresponding function value on those random variables. And by using the strong law of large number, we are getting the expectation of the given function. So function of random variable. So and what the expectation of square root difference between y and theta, that is the main expectation, is the variance of y. So that is the expectation of y bar minus theta is square is equal to variance of y. So we would like to be so hence we would like to this quantity to be as small as possible. So that means that y bar will be the good estimator for theta. So how? So in this case, we random variables, and so in the case when yi's are the independent random variables, so variance of y bar. What is y bar? Y bar is the sum, the mean. So sample means. So variance will be as those are independent. So variance upon y1 because those are identically distributed upon our number of sample. So if one way to decrease to get a small variance is increase the value of r. But that sometimes the simulation of random variables in real German computation is expensive and time consuming. So we'll see some techniques. So we'll see some techniques to get rid of this problem. So first we'll look into the first techniques that is called antithetic variables. So first suppose we have generated y1 and y2 identically distributed random variable having mean theta. Now look at those variance of y1 plus y2 upon 2. So this will be the variance of y1 upon 2 plus covariance of y. So one way to reduce the variance of this will be if the y1 and y2 are negatively correlated rather than being independent. So such a random variables are called antithetic variables. Random variables on the same probability space are antithetic if they have the same distribution and their covariance is negative, or in other words, they are negatively correlated. So, we'll see the use of those antithetic variable by using inverse transform method. We have some using inverse transform method. We are using inverse transform method to simulate xi's, and we are getting the function values at those points. And here ui are the uniform and 0 1. So for first time we are generating u1 up to un from uniform distribution 0 1, and then we are taking 1 minus un also, so that will also be the uniform distribution in 0 1. So we are again using inverse transform to generate the random variables, and we are getting the value yy. So the question arises whether y1 and y2 are the independent or though they will be negatively correlated. So first thing we can see that un and 1 minus un, ui's and 1 minus ui's are negatively correlated. And that correlation is minus 1 coefficient. So here the question arises to compute it in this way. If we computing yi's in this way, will they be negatively correlated? So the answer we'll find out soon. So first we'll see the theorem. If x1, xi's are identically independently distributed, then for any increasing function f and g and variables, the expectation of multiplication fx into y and gx is greater. Here x is this is greater is equal to the expectation of fx into expectation of gx. This equation is essentially the saying that covariance of fx and yx is greater is equal to g. So for the proof we will we'll use induction on n. So first we'll prove it for n is equal to 1. So for n is equal to 1, those variable will be one variable function. So if f and g are increasing function, then fx minus fy gx minus gy is equal will be greater than equal to for all x and y. Why is that? Because those are increasing functions, so both either will be negative, both the expression either they will be negative or they will be positive. So that will so therefore that this will follow that expectation that quantity is greater is equal to 0. So the expectation will also be greater than equal to 0 for any random variables x and y. So by using the just multiplication and linearity property of expectation, and keeping in mind that x is the same random variable as y, x and y are identically distributed, so we will get the expectation of fy is just the expectation of x. So we are done. For n is equal to 1, we are done. So now assume that the inequality equation 1 holds for n minus 1 random variables. Now for n random variables, we'll use the conditioning here for an nth component of those vector x of random variables. So expectation of fx into gx given xn is equal to xn will be just expectation of the we are putting xn at the and then by using the independenceness of xi's vectors we will get a expectation of this because f and g and these are independent vectors, so will xi's are independent vectors, so this conditioning just expectation of this. So this will be greater is equal to by using equation 1 for n minus 1 variables as we have assumed that, and then then we are using again we will get this expectation of fx given xn is equal to xn and expectation of gx xn is equal to xn. Hence by taking the expectation on both sides we are done, because we have already if we use the expectation again here and we'll use the case for n is equal to 1, we have proved equation 1, so we are done. So the corollary of that is if ui's are the identically distributed uniform 0 1 and h is an increasing or decreasing function on r, then rn, then the h of un and h of 1 minus un with covariance will be negative. That is just because h is increasing function on un, and then this h of this will be the decreasing function, so we'll get the minus h will be increasing function, the covariance of that will be positive, so minus will be taken out. So covariance of this will be negative. We got our answer from that, those yn here, those will y1 and y2 will be negatively correlated. So the answer is yes when the g is an monotonic function, increasing function. So first we'll see the one example here. So suppose we want to simulate the expectation of a exponential of u, where u is the mm, uniform random variable 1 0 1. So clearly we can see that expectation will be 0 e minus 1 here. From here we know that integration will be e minus 1. Now we'll look at the covariance of eu minus eu and e to the power 1 minus u. So here this is the negative, so see that eu and e1 minus u are negatively correlated, and that means eu is EU and e to the power 1 minus u are antithetic variables. Now we'll see that a variance of EU is just 0.2420. Once we use this expression, this estimator for mean, then we'll see once we are having u1 and u2 independent random variable, then we are getting the variance at 0.1210, where it's use the antithetic variable u and minus u, it gives us the variance at 0.0039. So see the reduction at the when we are choosing the UIs are independent, we are getting variance at 0.1210. But once we are using the UIs as antithetic variables, we are getting the variance at 0.0039. So this is the huge reduction, almost 90, more than 90% reduction. So this is the use of it. And the same can be used to simulate the reliability function. So consider a system of n components in which I is independently of other components work with probability this. So this is the probability of working of I PIs are the probability working of component, and let x size is the one if component size the work and then zero otherwise. So suppose there are monotonic structure function phi such that so phi is the structure function. So phi will be assuming the value one if the system works under these components and zero if otherwise. So we are interested in simulating the estimate the reliability function. So the expectation to get the expected value of the structure function is not so easy in the traditional way. So we'll use the simulation to get a reliability function, and then and will get the expectation of this structure function in a way so that the variance would be less. So we'll get so that we'll have the better expectation, better reliability function. So we essentially we are using the we are interested in finding the probability of probability such that the structure function is value of a structure function is one. So for this, we simulate exercise by generating random variables, UIs and uniform, and setting just like Vidit will be telling you how to generate the discrete random variables. So these are this is discrete random variable to generate exercise. So thus we have phi of x1 of x1 h is un. So in this way, we have instead of using this phi as the estimator, we'll use h of un, and here h is the decreasing function that we because of this condition the h becomes a decreasing function. That's why clearly we can use antithetic variable to raise our reliability function. Now, variance reduction by conditioning. So, what in this? So, we are done with antithetic variable. We'll look into variance reduction by the condition. So, let us recall the conditional variance formula. So, this is the conditional variance formula. Variance of any random variable can be written as the expectation of variance of y given z plus variance of expectation of y given z. So for some random variable z can we so this is the so we'll use this formula to reduce the conditioning. So now why? So if for some random variable z we can compute the expectation of y given z. So essentially we were interested in computing the expectation of y, but but if we are having some information about y given random variable z, and we can compute the expectation of y given z, then we can use this formula and we see that the expect and then and the expected value of this the variance of this is greater than follow that variance of this expectation value, and then since the expectation, so instead of using the y as the estimator for the we will use expectation of y given z as the estimator of y because expectation of y, because here we can see the expected value is if of e given y expectation y given z is just expectation of y, and here we can see the variance of this estimator is less than the variance of this y. So in this way we can use the conditioning. So it turns out that this is the better estimator for UI than Y. So variety of ZI can be conditions on the obtained to improve estimator. Each of these estimators will have mean, EY, and a small variance. then y. So first, we'll see the proposition. So here we have seen that we can condition on one Jedi. In general, we can condition an n number of Jedi's on y. So for such that for any lambda is greater than 0, such that lambda is a summation of lambda is a 1, then the expectation of summation of e lambda I expectation of y given z I is equal to the same. So we can use this as also the expectation of y, and variance of this will be less than the variance of the. So any linear combination of expectation of y given z I will also be used, can be used as the estimator of the y, and which has the minimum variance thereby. So proofs of first one is obvious. We can see that by linearity of expectation, we will see that that will become inside and then lambda is, and this become expectation of y. So because summation of lambda is that it's called summing to one, so we will get an expectation of y. And or we let any integer values random variable independent of all other random variable under consideration. So, and we are choosing a random variable n which is independent of all other like y and z's random variables, and such that the probability of n is equal to ni is just lambda I, those lambda I. So this n will be the proper random variable, as we can see the summation of lambda is 1. So this is the proper probability mass function for n, and by using 3 twice, 3 what is 3 there, so 3 is this equation, the variance of expectation of y given z is less than variance of y. So we'll be using that twice. So variance of y will be greater than variance of expectation of, then again there is using, and then we are done. Suppose that now example. So in this example, we'll use the simulation to estimate pi using simulation. Suppose that the random vector is uniformly distributed in a square of area 4. So xy is the random vector which is uniformly distributed on a square of area 4 center at the origin, and then we'll have the probability that xy will fall inside a unit circle will be that pi by 4, the probability, because the unit circle will have the radius 1. So pi r square, that is area of circle upon area of square, so pi by 4. So now if u is uniform in 0 1, then 2u minus 1 is the uniform in minus 1 to 1, just algebra. Therefore we generate random variable numbers u1, because that square will having the one x-axis at minus 1 to 1, y-axis minus 1 to 1, because that is centered at 0. So we are using the uniform distribution between minus 1 to 1 to generate a random point in the square, inside the square. So so we are using x as to u1 minus 1 and y is to as u1 minus, and defining I is equal to 1 if that x square plus y square is less than 1 and otherwise 0. So we are choosing uniform random numbers from 0 1, and we are setting it at 1 as x as to u1 minus 1, and then we are saying that if x at y is equal less than is equal to 1, that is x and y are falling inside the circle, then we are, this is the indicator function for the circle inside the square. So is one and the other. So now we are interested in a expectation of this random vector. So this is also a random vector. So random variable. So we are interested in the random variable expectation of random variable, just the probability of the random vector follows in, fall, falls inside the circle. So which is pi upon 2. The use of the average of succession value of y to estimate y can be improved upon by using expectation I given of I given x rather than I. So one way we can, what we can do, that we can take a number of samples and we'll estimate the expectation of y by using uh, the independently. But we can, here we can use the conditioning to improve our that estimator. So Now we estimate the expectation of I given this is the conditioning here. So we are conditioning that for given x is equal to x, will estimate the expectation of y I. So this is the just calculation. So here we'll see that the probability, this will be the probability of y square is less than equal to 1 minus x square, because x and y are independent. So here we'll see that that y will be in between this, and but here y is the uniform random variable will be minus 1 to 1. So we'll see that by using the formula, that is the, this is the probability mass function for y, and this is the limit. So this will be just 1 minus x square. So what we in variance reduction by conditioning, we want to know that expectation of I given some random value. So we are here we are able to calculate the expectation of it. Now hence expectation of this is equal to this. So now we'll further get an expectation of this. So expectation of this is just this, because x is the random variable, uniform random variable in minus 1 to 1. So the expectation of this will be this, and this is just now this becomes the expectation of 1 minus u square, where u is the uniform in 0 1. So now I'll see that improvement in the variance obtained by using the estimator over the. So now we'll see the variance of this quantity. So variance of this quantity is 0.0498, whereas the variance of y. So what we got that instead of using I as the estimator, will use 1 minus u square to estimate the pi 4. So the, because variance of this 1 minus u square is 0.0498, whereas the variance of y was initially was 0.1686. So it shows the 70 over 70% reduction in variance, but it can be further improved. So here we are using the estimator of this. It can further be used here to get estimate, to get a estimator which is lower than the variance of this. We can use further use antithetic variable to reduce the variance. So and this is the variance reduction by conditioning. Now I'll look into the control variates. Now suppose that for some function f the expected value of x is known. So control variates. So in a suppose, and say E of fx is equal to, then for any constant a we can also use w is equal to gx. So essentially we are trying to estimate the expectation of gx, but for a given random vectors x, whose is having the joint distribution. So for this one, we what we are assuming here, we are saying that if we have a function whose expected value is known, then we can use this w as an estimator of gx, which has the lower variance than gx, because the variance expectation is an estimator of gx, because expected value of w is nothing but the expected value of gx, so we can use. So we'll decide for which a the variance will be lower. So this is the first we will calculate variance of W by using the formula variance, and then this will be minimized by using the differentiation first order derivative, and then so for this a particular value of a the variance will be minimum, and that variance will be less than the variance of this. So as we can see here, variance of W is equal to variance of Gx minus covariance of Fx Cx square upon. So when the variance will be uh, slightly lower than the variance of GX, when the stronger the related correlation is between FXG, and then the lower the variance of W, rather of variance of GL. So hence the use of control value greatly reduce the variance of the simulator whenever axes are strongly correlated. The quantity fx is called control variable. Here this one, small fx variates for the simulator, for the simulation estimated Z. So we will do example one by using control value. So we have seen the example one of estimating the exponential of u, value of and estimation of exponential of u. So here we'll use u as the control variable. So u here we are using control variable. So g of x is g of x is equal to e to the power x, and f of x is equal to x here. What we want here, g of x, for g of x we are giving exponential of x, and we are taking f as x, f of x is equal to x. So we are calculating the covariance of between gx and fx. So here this is the covariance 0.14086, and we know that the variance of u is 1 by 6 because u is the mm, uniform number variable. Then by 7 we have variance of eu plus a star u minus r is equal to variance of u minus this. So this will be the variance of this estimator. So this variance of u, just it was 1 by 2, not 1 by 2. So it is calculated. So this is 1 by 2. So this is the w for this. And so we'll see that the variance is 0.0039, which was also in the antithetic variable case. And for example 2, which was the simulation of reliability function, that is expected value of the expectation of the structure function. In that one we can use the control variate of x1 x2 x, and that control variate for uh, structure function, this f is the just the number of components which are working, and we'll see that and we can do the completion. Now the fourth one is the important sampling. So let us see the random vector. So what we are doing is, the random vector has been joint distribution density function is, and suppose that we are interested in estimating this what we are doing essentially. And where the proceeding is an n-dimensional integer. Suppose the direct simulation of the random vector x. So as to compute value of hx is inefficient, uh, possibly because it is difficult to simulate the random vector having density function effect. The variance of hx is large combination of those. So to overcome this difficulty, we can take another probability density function gx such that fx is equal to 0 whenever gx is equal to 0. So instead of using the hx, we'll use the instead of using fx as the joint density function for random vector x, we'll use gx as the joint density function for x, and expect. So and we'll calculate the expectation of hx into fx upon gx instead of expectation of hx. So it is if the density gx can be chosen so that the random variable has a small variance. So we are and then this approach is referred to as important sampling and can result in efficient estimator of theta. How to select an appropriate density function here. So so a density function, this ftx is equal to exponential of dx fx upon mt, where it's called tilted density of f, where mt is the moment generating function of x. So if we use this tilted density function for important sampling, then we can get so here for gx we can use this tilted density function. So if f is the exponential density with rate lambda, then ftx, because this is the exponential density with rate lambda, then what will be the ftx? So e to the power tx, fx will be lambda equal to minus lambda x, or and mt will be, so here is the empty. So this is the tilted density function for the exponential density with rate lambda. The finally we'll see number of runs. That means number of how many samples we need to estimate the expectation, so that the variance is reduced. What variance is, what is we want. So we'd like to choose R, the number of necessary runs. large enough so that the sigma square are acceptably small. But sigma star, this variance is not known in advance, so we'll use the sample variance. So for that we need to sample from samples, so say k samples, and we'll sample the variance and then we'll calculate this value. And so for the to get the actual precision, we'll increase the sample, so we'll get the required precision. Thank you.